Okay, so hello everyone. Hello from CIRA for the Cooperative Institute for the Research in the Atmosphere here in Fort Collins. And what we're going to talk today about is about the GDI, the Galvez-Davison Index, how the GDI is calculated and how we can apply it to improve the forecasts of convection. So in this case, we're going to focus mostly on convection that is happening in mid-latitudes. The GDI was developed for the tropics. However, it does work in mid-latitudes as well. So I'm going to start with the satellite loop showing, first let's start with the geocolor to have an idea of the general systems that are present at this time. Okay, so the geocolor product, the satellite imagery, kind of gives us an idea of what we would see if we were on on an aircraft or on a spaceship or on the satellite itself, right? What the human eye would see. So we can see different colors of the land, the terrain. You can see the green terrain in Texas and the southeast US, and then how dry it is in the Rocky Mountains. And you can also see the different types of clouds, right? However, to get a better perspective of what type of clouds we're seeing, it's good to use other products as well. So there are many products we can use. One that I really like and I use very often is the day cloud phase distinction product. This one here. So we're gonna use it during this short session to evaluate different types of convection. So in a nutshell, with this product, you can have an idea of where you have water clouds and where you have ice clouds. And I'll talk a little bit about that later. So let's go to the presentation of the GDI. And the GDI is a stability index that we developed, Mike Davison and I developed at the Weather Prediction Center in 2014. So the goals of this presentation are first to revisit the science behind the calculation of the GDI, then to emphasize the role of its subindices, and then to show the importance of integrating complementary tools to optimize GDI applications and an analysis of atmospheric dynamics and moisture availability. So um, the GDI is pretty good to detect the environments favorable for convection, but it's very important to also integrate other fields, and analyzing the dynamics is super important. Then we will work also on applying the concepts learned to evaluate the regions of convection occurring right now. Okay, so what is the Galvez-Davison Index? The GDI is a stability index that was developed by NOAA's Weather Prediction Center in 2014 to improve the forecast of tropical convection. But it also has skill in the exotropics as well, where warm and moist air masses are present. Therefore, it can help US forecasters gain confidence when forecasting impactful rainfall events. If the GDI is very high and you're forecasting a rainfall event, and then you look at all the different variables and then align with a potential of heavy rainfall, then your confidence increases. Now, the GDI describes whether the environment is ready to host shallow convection, deep convection, or convection with a heavy rain potential. And this is the website where the official GDI information is available at the Weather Prediction Center. However, there are several institutions that have already coded the GDI in their systems, and there's also private companies that are running the GDI on different models. So this is how the GDI looks for today. This is the current situation, and you can see that we have we can see a plume of higher GDI in the plains. If you remember, there was convection going off in the central plains of the U.S. You can also see a plume of high GDI going off, present in the Mississippi River Valley. Remember, we had some convection, and if you remember, there was also a lot of cloudiness in the northeast U.S., but the GDI is very low there. We'll speak about it in a second. Okay, so what can the GDI detect? The GDI can detect a lot of different things. So this is a graphic that covers, this is actually the current situation. I did this with yesterday's forecast. So this is a forecast, but you can have an idea of what the different systems that are present in the Pacific and the Americas. So you can see, for example, the ITCC, the Intertropical Convergence Zone along the entire Pacific and monsoon trough into Central America. You can also see the ITCC in the Atlantic. Then you can also see fronts. So the GDI can detect some fronts as well. You can see these different fronts. This is very likely a front with the South Pacific Convergence Zone. Then you can also see areas where you can have a potential for heavy rainfall. So when the GDI is very high, say more than 45, your potential for heavy rainfall increases. And you can see first, you can see the warm pool convection in the Western Pacific right here. And then you can also see very high GDI present in Central America at the moment and southern Mexico. And embedded in this region of higher GDI, we have Tropical Storm Eric, right? Yeah. So the GDI is capable to capture these environments. It's also useful to capture really dry areas. So for example, you can see GDI is extremely low in the Western US. This means that the chances for rainfall are very little, and very likely most convection you're going to get is going to be shallow convection. And also you can see this in front of South America. These are the impacts of the subtropical anticyclones. All right. Now, the GDI is also a great tool to track tropical waves, and it also captures the convective structure of well-established cyclones. So if you go back, you cannot really see the structure of Eric here because Eric is still trying to organize at the moment, and this was a forecast from yesterday. However, this is an example of other cyclone. This is Cyclone Mindul in 2021, just south of Japan. The GDI is pretty useful to see the convective structure of the system, but it's also useful to see the feeder band. And feeder band convection can be very significant, can produce very significant rainfall with tropical cyclones. Then tropical wave tracking, of course, you need to look about other tools. The GDI alone is just speaking about the convection associated with the wave. However, you can, if you combine the flow and the GDI, it will help you visualize where these axes of convection that, for the most part, are associated with tropical waves are. So you can see one here. Let's see, one propagating here, and then another one propagating here towards Central America in this particular example. All right. So why develop the GDI? By 2013, no stability index could properly detect environments suitable for tropical convection. Most indices failed, and the one that did the better job was the K index, developed in 1960 by George. And what we wanted to do is to go something like this, like a very broad area of high index value and convection very discrete embedded in that area, to something like that, to something more precise, where the index matched better where the convection was forming. So if you go here and look at the image on the right, you can see how the different indices did in representing this situation. So what is this situation? This is an average of 12 hours of cold cloud tops over most of the Caribbean basin and northern South America, and you can, in Central America, and you can see that uh, values that are higher, values that had a lot of cloud tops during the period of very cold cloud tops, and those are associated with convection. So we can say, okay, these regions that are in this white contour, if you can see it, are regions that had a lot of convection during this period, right? So we want to see if the indices were able to capture that area of convection. So if you look at the lifted index, it didn't work. No, it wasn't able to capture that. The Cape actually did kind of the opposite. In the Caribbean, the Cape was very high where no convection formed. Then the total totals also didn't do a really great job. And then the K was much better at representing the region where convection occurred. So we wanted to develop something better. And if you look at the GDI for this situation did a really good job. It, of course, it misses some areas, and it also depends on which database it is calculated on. So in this case, the GDI was calculated with the GFS. However, considering that all the indices were calculated with the same database, the GDI was the one that was able to capture the situation better. All right, so processes that the GDI considers. The GDI considers three processes. The first one is the availability of heat and moisture between 950 and 500. So if you look at the calculation of the GDI, it is using these levels. It is looking into the low and the mid troposphere. It's not looking higher up, because most of the moisture and the processes that are involved in the triggering of convection occur mostly in the mid and the lower troposphere. So we're looking at these four levels: 950, 850, 700, 500, and 500. So the first index is the CBI, so it looks at the availability of heat and moisture, and we use theta E, equivalent potential temperature, for that. Then the second index is it's called the MWI, or the mid-level warming index, and we're looking at the stabilizing impacts of warm mid-levels. And then the third one is the inversion index, II, which is looking at the stabilizing and drying impacts of temperature inversion in trade wind regimes. So the GDI is just an algebraic sum of these three indices. The CBI is the one that provides, say, the fuel for the GDI, or speaks about the moisture and the heat available. Then you have the MWI, that it will decrease GDI whenever you have these stable conditions associated with warm air masses in the mid levels. And then you have the II. The I is a little bit more complex, but it will also decrease the GDI. Okay, let's go index by index. So the CBI, the column buoyancy index, as we mentioned, it describes the amount of heat, moisture, and buoyancy in the column. That's what it's called, buoyancy. So the higher the CBI, the more buoyant the column, the more heat available, the more moisture, and the larger your potential for convection. Therefore, the GDI, the CBI, high CBI usually relates to high GDI. Now, this is the only subindex that has positive values. So we need the CBI for the GDI to be high. All right, let's keep going. Now, the mid-level warming index, this describes the stabilizing impacts of warm mid-level ridges. As we mentioned, if you have warm mid-levels, the convection that's forming is going to struggle to become robust. Whereas if, let me animate this again. Whereas if you have cool mid levels, that usually associates with a more unstable environment in the mid troposphere, and the convection will tend to be more robust and will have higher chances of producing heavy rainfall. So the warmer the mid levels, the more negative MWI becomes, and then that makes the GDI lower. So the impacts of the MWI, if you have very warm mid levels, are like limiting the strength of convection and also the coverage of convection. Now, the third index is the inversion index, the II, and this index does two things. It describes the impacts of stabilization and also dry air entrainment associated with trade wind inversions or temperature inversions in the lower troposphere. These are very common in the trade wind regimes. For example, in the Caribbean, in the southern U.S., particularly in the warm season, Central America, these inversions are very, very prominent, very important, and they play an important role in modulating the type of convection you're going to get that day. All right, so uh, this index can also only be negative, so it will limit the GDI. And whenever you see really low values of GDI, it usually comes from the inversion index. The inversion index plays a very important role in lowering the GDI. So if you look at the image here on the right, if you have no inversion, we're still assuming that the CBI is high, right? So the GDI is also high, say it's 45. So you get cells growing into the entire troposphere. But if you have a strong inversion, you will see that the cells try to grow and they cannot grow. So they start expanding horizontally. Whatever can go through interacts with the dry air and dissipates. And if you're somewhere in the middle, you will get some growth, but also some dry air entrainment processes. The cloud is going to struggle to grow. You're going to get some dry air entrainment, and at the very end of the day, your precipitation is not going to be as heavy. So the trade wind inversion has a very strong impact in limiting the GDI. Right, so GDI value interpretation. So a general interpretation color scale is commonly used. We usually use this scale. It's been adopted by many places as well. So whenever you see grays, usually and maybe blues, usually means that the GDI, it means the GDI is low, and it often relates to an environment that is only able to host shallow convection. No, so the chances for deep convection are very low. Now, whenever the GDI starts acquiring higher values, and in this color scale starts turning green and yellow, that means that your chances for deep convection start increasing. So you may get a couple of of deep convective cells embedded in a field of shallow convection. But once you start getting oranges and reds, meaning the GDI is higher than 35 or 40, then your chances for deep convection are much, much higher. You get a very high chance for deep convection, and even you can develop a potential for heavy rainfall. Hey Marshall, how are you? So the question for Marshall is, how do we know when the GDI uses GFS or otherwise, since it did a better when you use GFS fluffer, as you said? Well, you have to know where the source of the GDI is to know what it was calculated with. So the GDI that is available at the NOAA website is all calculated with the GFS. What I'm presenting here is also calculated with the GFS. So if you want to look at the GDI with other databases, you might have to explore other options. There are other websites that calculate the GDI with other models as well. If you want to take a look, so I can pass you this link later on, but basically there are private companies that have coded the GDI in the European model, in the Canadian model, and in others. So that's another option. But for the most part, whatever you see online, at least at the NOAA websites, is calculated with the GFS. Yeah, Christian.
Hello, Jose, and everyone. Good
Hi,
morning.
Christian.
Thank you for the training. I have a question about the GDI, especially for the values on the mountain range, especially the Andean and some small mountain range that we have in Ecuador. So in this case, how do you consider or analyze the GDI in these parts when you have a topography, orography very high, because you use a lot of information in low level of troposphere. So in this case, what do you recommend?
That is a very good question. And yeah, so if you think about the applicability of the GDI, so it shouldn't work in elevated terrain just because what you said, right? It's calculated with values that go all the way down to 950. So it is true. Once you go really high up in a mountain range, really the GDI is you need to be a little bit careful. However, models they do contain some degree of information of what's going on in say if you're using a 950 hectopascal field in the GFS over Quito in Ecuador, and Quito is much higher, right? Quito is probably close to 700, right, hectopascals. So if you use a 950 value on the model, in reality that value doesn't exist, right? However, that information that the model contains on that 950 level point does contain certain degree of interpolated information that could be useful to forecast convection. So you have a little bit of useful information in that grid point, in that fake grid point, even though in reality it doesn't exist. So if you do apply what we developed, the terrain correction, I'm going to go back to the presentation. I don't have the formula here, but it's on the paper, on the article, and the article is on the website. So if you do apply the terrain correction, you should be able to play a little bit with uh, to maximize the use of that information that is on that grid point. So the terrain correction actually helps with mountain ranges. But then again, if you go really high up, the GDI doesn't work. I would say that in places like Quito, places that are at 850, 700 hectopascals, the GDI could work. But once you're higher than that, yeah, the index doesn't work very well. So the terrain correction will help with that. Yeah, thank you, Christian. And also, I want to make sure that you all know that the was developed. Terrain correction was developed with GFS data because we did develop the GDI looking at GFS analysis and comparing them with satellite imagery and other fields. So this is tuned to the GFS. So if you're gonna code the GDI in other models, it is important that you modify this according to your needs. So this is basically adapted for GFS analysis and forecasts.
Okay, thank you, Jose. And another question related to that.
Yeah.
In the other wave page that you that you watched to us, that you presented
Mhm.
to us, and they calculate the GDI in other models. In these cases, you know if they have terrain corrections for it or
That is a
no.
very good question. I would think that they do. But this is a guess. So my guess would be that they are using the terrain correction that it is on the paper. I'm going to go to the paper right now. So if you go to the main GDI website, oops, there you go. This is the PDF. Yeah. So I assume they're using this formula with these values that we develop. No, I assumed that's how they're doing, but I don't know. I really don't know. But you can see how, for example, here, look at the U.S. and Mexico. You can see the Rockies and the Sierra Madre Occidental in Mexico, and you can see clearly how this is the European GDI, the ECMWF. Here it is. Okay, ECMWS GDI, right? So you can actually see how these are very sharp, which are not as sharp in other models. So I assume they're using the GFS correction. And speaking of, since we're doing this, we can actually we can see we were talking about a lot of convection in the central plains of the U.S. and you can see that the European GDI is also capturing that potential, at least just right now, and is also capturing the moist plume located east of the Mississippi Valley. So, let's do a quick review of the current situation with the GDI. So we're going to use satellite products for verification. And a product that I really like among many, and I was showing at the beginning of the session, is the day cloud phase distinction RGB. This RGB helps to detect water clouds, greens and blues. And this is not today's situation, FYI. This is another situation, but this RGB detects water clouds and also ice clouds with yellows and reds. So in this RGB, deep convection looks like round yellow features often growing with time. So in this particular example, you can see this convective self growing and this would be in southwest Louisiana. So Louisiana is getting a lot of development uh, of convection during this period. Now, yellow means thick ice clouds. So what happens is that when clouds are growing vertically, when they're developing vertically, eventually they reach a layer when it gets really cold and they start to develop ice. And ice looks yellow in this RGB, yellow or red. No, and this has to do with the way the RGB is formulated, right? So in this case, yellow means that clouds has ice and is thick. And the round shapes tell you that it is a convective cloud. So if you look at these little clouds here, you see that they start light blue, they have the little dots green, and then they turn yellow. So basically what is happening is that the atmosphere is losing stability and then convection is starting to form and it's starting to grow vertically. This is what is called convective initiation. So this RGB is great to to see convective initiation occurring from the satellite perspective. So we're going to use this RGB to verify the GDI. All right. So this is another example. With this RGB, in this case, I also included lightning. So this is the GLM optical energy density. This is all data from Cirrus LiDAR, uh, and um, and what I wanted to show with this is later in the day, is that you can see that the cloud tops turn red as you go into the evening. And the reason why the convection, the cold cloud tops turn red is that the green and blue components of the RGB, there are reflective bands, the 0.64 micrometer and the 1.6. So when the sun sets, this become black. The data disappears. So the only data you will get is data from the red component of the RGB, which is the 10.3 micrometer band that gives you information about the cloud top temperature. So at night, this RGB is not very useful, but you will still see the cold cloud tops in color red. All right. Okay. So the question is the GDI capture all areas with deep convection? This is just another example. And if you look, I encircled the areas of deep convection. Well, the areas where the GDI did a good job with these white contours, and you can see that for the most part, GDI is able to capture areas of deep convection. So A, B, C, and D and E, well, deep convection occur in all those areas. But the index is not perfect, and it also depends on the database it's calculated on. In this case, we're using the GFS. So if the GFS is wrong, the index is going to be wrong. However, also the index is not perfect, and there's other things happening. So look at Texas. The GDI is saying that Northeast Texas has a higher chance for convection, but if you look at the image, the convection is actually almost in Brownsville, Corpus Christi in southern Texas. And also here, just north of Cuba and west of Florida, nothing happened. So why? It could be that the database is wrong, but there's also other things that we need to look into that could be of use, like the dynamics. So let's talk about the importance of considering the dynamics and moisture product. Let me stop here for a second. Let's pause and let's analyze the satellite imagery quickly using the GDI. So you can see the GFS GDI for right now, and you can see that there's a lot of convection in the plains going off. We're here in Colorado, so just northeast of us, there's a lot of deep convection going off. Actually, there's a chance for severe weather later today, but the GDI is not designed for severe weather necessarily. Right, it could help you a little bit with the part of the moisture content and how much rain you might get, but it's not designed specifically for severe weather, say tornadoes, strong winds, and large hail. It's not designed for that. But so you can see that we have a lot of convection going off in the plains, but you also have a little bit of convection in western Oklahoma and Texas, and you can see that the GDI is capturing this plume. But if you look at the GDI alone, you would think that you will have a convection evenly distributed, right? So uh, even though the GDI is capturing this whole region of convection, the convection is organized in a different manner, right? There's much more convection and stronger convection going off in northeast Colorado, Nebraska, and parts of Oklahoma and Kansas. Then the moist plume along east of the Mississippi Valley, I think the GDI did a pretty good job there, but also the deep convection is happening in a very isolated manner. These oranges and yellows, whereas most of it is shallow right now. So if you look at the GDI, you would probably forecast deep convection in Kentucky, but Kentucky right now doesn't have much deep convection. So we're going we're going to look into why is the reason why that's happening. So I need to accelerate a little bit the time, and I'm just going to jump into the dynamics. I had some slides speaking about the importance of considering the dynamics, but given the limitation of time, I'm just going to go ahead and look at the current situation. So if you look at the current flow pattern here on the left, we have the winds average in the 400 and 200 hectopascal layer. So this gives us an idea of what is going on in the mid and upper troposphere. Well, mostly the upper troposphere. So what we do have a very robust upper trough that extends from Montana in the northwest U.S. across Colorado into New Mexico. And usually when you get these troughs, you get a lot of weather, ascent, and if you have moisture, convection east of the trough. So this is consistent with what we're seeing with the convection going off in Nebraska, Kansas, and parts of Oklahoma right now. Then to the east, we do have another upper trough that extends from Illinois, just west of the Mississippi, and then extends all the way into central Mexico. And the same, ahead of this trough usually is where you have most ascent and more weather. If you look at the GDI on the right, here we have the GDI, but we have overlaid 1,000 to 850 hectopascal winds, and you can see that this gives additional information. So you can see that in this case, the winds, if you look at the plains, you got southwesterly winds in Texas, Oklahoma, but once you get to Kansas, these winds break, right? And in Nebraska as well. So this is a region where you will likely have low-level convergence, right? You're ahead of the trough, looking here on the left, you're ahead of the trough, and then you're in a region of low-level convergence. So the dynamics are favorable for more convection here than if you were, say, in North Texas. So the dynamics are very, very important. So what I'm going to do, I'm going to go a little bit further, and then what we have plotted here is a low-level convergence. In this case, it's low-level moisture convergence, low-level moisture flux convergence in red, And also we have plotted upper divergence in light blue. And you can see that the dynamic forcing for the central plains of the United States, it's important. Therefore, the atmosphere has more potential to be able to use the GDI here than if you were in Texas. Now, if you look at the moist plume that is located along the Mississippi River Valley, uh, so the upper tropospheric pattern is not as impressive. You do have some upper divergence as well ahead of this trough, and you can see the winds are speeding up around this ridge. So you do have an area on upper divergence here, but your low level moisture convergence is a little bit more limited. However, the GDI is high enough. So I would expect that the strongest convection is going to continue developing in the central plains of the US, and we might see some more convective development later in this region. To finish, because I'm running late and it's already 35 past the hour, I'm gonna look at the Tropical Storm Eric. So in this case, you can see that, well, you can see the flow rotating around Eric according to the GFS, and moisture convergence. The red contour is very prominent in this region. So you have everything. You have high GDI, you have a low level moisture convergence, and if you look at the dynamics, you do have an upper ridge that is located a little bit to the southwest of where Eric is located. Eric is right now a little bit to the south of Guatemala, but these upper ridges are favorable for tropical cyclone convection because they usually associate with weak vertical wind shear. No, tropical cyclones like weak vertical wind shear, and it also associates when it has upper divergence. So this is a very different environment, but this is another region where, of course, we would expect very heavy rainfall associated with the feeder bands of Eric. And with that being said, I'm gonna, for the sake of time, go back to the satellite imagery, and we can see the convection in the plains. As we spoke, not a lot in Texas. Let me go. Yeah, well, just this. Not a lot going on in Texas. The bulk of it is happening in Kansas and Nebraska. Then this moist plume also uh, starting to develop some deep convection here in the Mississippi Valley. There's a lot of clouds, so the diurnal heating is struggling, but later on in the day with this high GDI, I would expect more development. And then you can see Eric looks really robust right now. Convection is starting to wrap around the center, and there's also some feeder band convection and southerly flow. Southerly flow is dangerous for South and Central America, so you can see some southerly flow occurring just to the east of Eric. And with that, a little bit late, but I'm going to open the room for questions.
I have inquired about the GDI, and if you or someone else made a kind of verification, uh, how with a statistical significance, how well fits the GDI with the severe weather events. Do you know about something about it?
No, I actually haven't. I don't know about that. I mean, there are several papers on the GDI, but let me go back to this. There's several papers on the GDI, but I don't know if there's any paper that has looked into severe weather with the GDI. I would think, yeah, it's a good question. I can pass you this link. Well, this is my personal website. Maybe I shouldn't be doing this, but I have the compilation of the papers here if it's useful, so I can put it on the chat. There's a list of papers there that have looked into the GDI, but I don't think there's any paper that has looked into in, in, into severe weather with the GDI. I think that would be a great idea to look into. I envision that you will have to consider the GDI as an additional parameter combined with other ones. That's what I would assume. But it's just I'm just jumping to conclusions.
Yes. And also identify which model fits better with the GDI index. It could be
Right.
not only the GPS, but yes, a good idea to work in the future.
Yes, it's a great idea, and yeah, that's a very important comment that you made because definitely the GDI is going to depend on the database you're calculating it with, and yeah, and sometimes you would say, okay, the GFS say this particular model works much better than this other model, but in occasions it that will not be true. That will switch, right? So there's also certain situations. It also depends on the synoptic situation. It also depends which model. Sometimes a particular model is very good at initializing and representing processes, but here and then it will really fail and the other model will become better. So it's kind of tricky. So I think it would be very useful to look into that. Yes. Yeah, go ahead,
Hey,
Jeff.
Jose, it's Jeff. Quick question. I'm doing some research kind of in Madden Julian oscillations and, of course, its impact in the tropical weather. With this broad divergence and convergence patterns, I guess that impacts the lapse rate, um, creating the atmosphere more stable or more convective, and that would be reflected in the GDI.
Yes, I believe so, for sure. I believe so. Yeah, I haven't looked at it with detail, but I believe is that whenever you have say an upper divergent MJO, what it will relate to a higher GDI. Why? Because you are it's like right now. Let me l- look at this for a second. Six tropical. Okay, this is confusing me, but anyway, I was expecting something green here. But in previous days we had a lot of upper divergence, which kind of helped with triggering this situation in Central America with a lot of moisture, right? If you see June 13, we had apparently a Kelvin wave MJO, like large area upper divergence. Right now, the upper pattern it appears to be switching. You're starting to see upper convergence. But going back to your question, yes, whenever we have a period with a lot of upper divergence associated with the MJO or a large and potent Kelvin wave, what will happen is that enhanced upper divergence and enhanced low level convergence, they will start to trigger more convection. And
Oh,
whenever
that's
you get
cooling the column,
right, well,
decreasing the lapse rate, so making it more convective unstable, right?
if you decrease the relapse rate, it becomes more stable, right?
More unstable.
Oh, okay, making well on the long run that will warm up the upper troposphere, right? You will get latent heat release will warm up. So
From the convection, yes.
from the correct from the convection, yes, 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 yes. So anyway, the fact that you're piling up all this moisture and generating all this convection will lead to an increase in GDI.
Right.
Yes, yes. So yes, the answer is yes. And going back to and this is what we're seeing right now. So look at all this convection going off in Central America and in the Eastern Pacific, and let's go to the GDI. And you can see all these large region of very high GDI values. So that is, to me, that is partly in response to how upper divergent the MJO has been in previous day. Now it's switching, but that uh, uh, to me that's partly related to that. Yes.
Right. All right.
Yeah.
Talk at you soon. Thanks a lot.
Thank you. So Marshall, okay, okay. Will you be sharing information, rainfall intensity projection, etc., when a tropical cyclone poses a threat to Dominica? Well, that's a little bit beyond the GDI, but you can ask me, and I can give you my point of view. I am not at the international desk anymore, so I don't have the responsibility to do the IDSS, so I'm not involved in that. They are the ones doing the rainfall information for the cyclones. But if you want my personal perspective, yeah, let me know and I'll be happy to give it. And thank you. I'm also reading that Marshall saying that being using GDI has been performing very good for me. That's great. Yeah, it works really well in the Caribbean in particular. I assume you're back in Dominica, Marshall. The GDI was developed for the Caribbean and for trade wind regimes, really. But as we saw in this session, it also works in the extratropics during the warm season because we have our masses that are more tropical-like. So right now, it's working in the U.S. for the most part. But once you get to the extratropics, just to again to wrap up the session, once you get to the extratropics, the role of dynamics becomes even more important than in the tropics, right? So in the extratropics, like in the United States, it's even more important to consider atmospheric dynamics to make a good forecast using the GDI because the dynamics have a stronger weight than in the tropics. And that's it. Thank you, everyone.